So this is Kuni Inoue, who some of you might remember or have heard about his work. He spent 10 years at Wisconsin, actually. So when I first met him, he was just finishing up a forestry degree, and he transitioned, well, actually I know what I should say. Someone showed him Holton, and he really wanted to understand what was in Holton. And so he went into atmospheric dynamics and worked with a couple of the faculty members here. He did a little bit with Lou and Matt, and then he came to me and ended up settling on working on tropical convective variability. And he did a master's degree in 2000. His undergrad was 2010, master's was 2014, and the PhD was 2016. Then he's been at GFDL he was at GFDL for 2 years, doing a postdoc there, and now he's a NASA postdoctoral fellow at NASA GISS and Lamont Doherty Earth Observation. And he's continued to work on some things that are related to what we did for our PhD work, for his PhD work. And so we're here to talk with him. I invited him to come talk with my group about some of the more recent stuff that he's been up to. And yeah, we're excited to have him. So he would agree to give this seminar, and he's giving the same seminar at Columbia University next week. So you guys are getting a taste of what their seminar series looks like as well.
And it's going to come in on YouTube, maybe.
And it's going to be on YouTube in both cases.
I think so, yeah.
So you can compare. Actually, he suggested, since this one's first, that you guys not compare. But we get him live, too.
Nice.
So let's thank Kuni for being here.
Okay, thanks for the nice introduction, and then thanks for having me here. I'm very happy to come back here. When I was living in Madison, I thought like Madison was okay, it's kind of cozy town, everything is manageable. And then after coming to Princeton, I felt like Madison is awesome. New Jersey is terrible. And now I have a different opinion because I'm living in New York City, but still I think the Madison is a great city, so I'm very happy to come back here.
Did you live in New York City a long time ago also?
Yeah.
Oh, wow, yeah, okay.
Yeah. Well, yeah. Yeah. Anyway, yeah. So today I want to talk about the very simple model which represents a tropical convective variability. And then it's completely the thermodynamical model, and it's very simple. And we try to use this simple model to explain the convective variability. And this is the extension of my PhD work. And this is also the collaboration work with Michela Biasuti at Columbia University, and then also the Anne Friedman in NASA GISS. Okay, so first of all, I want to show this movie. I don't know how. Okay, here we go. Do you know how to play the movie?
Just click on it. Yeah, try to click on it. Nothing. Double click.
Okay, maybe I don't have to. Okay, but that's fine, yeah.
Oops.
Yeah, that's fine. Okay, so I tried to show the movie, but I couldn't. So what I'm interested in is this guy's, this is a global cloudiness movie, it's supposed to be a movie, and this is the OLR from the geostationary satellite. And then what I'm interested in is the tropical convection around here and here. And maybe you can see the cluster of the convection here. And then this is actually called the Mendelian oscillation, and then which actually moving to the east very slowly. And then this is very interesting and exciting phenomena. And then a lot of people spend their whole life to just study this phenomena. And maybe there is no tropical cyclone, but here is a kind of like signal of the diurnal cycle here. So we try to understand those kind of convection using a very simple model is my goal. So my question is how, first of all, can we advance our understanding of the tropical convection? And then my favorite approach is just simplify and simplify. We want to deduce a very simple model which represents a tropical convection, but this model has to answer those three questions. The first question is when the convection amplifies or decays, or in what kind of condition the convection amplifies or decays. And the second question I want to answer is how fast convection amplifies or decays. We want to compute the rate of the amplification of the convection using this simple model. And then the final question I want to answer is what are the main drivers of this convective amplification and decay. Maybe the surface fluxes, radiation, the vertical advections, etc., etc. We want to pinpoint what actually drives the convective amplification and decay by using this simple model. And first of all, I want to think about this question. Why do we need to know about moist convection? Like people say that because the convection is interacted with the large-scale circulations, and it's so important because like you want to understand the Hadley circulation, which has a lot of implication. You know, in the global warming, we have a lot of uncertainty about the convection, blah blah blah. But here I want to say that the most fundamental reason why we need to understand the moist convection is if we don't understand the moist convection, we cannot simulate the climate model, or if we don't deal with clouds in the model can blow up. And then I'm gonna explain why this happens. This is a well-known schematic figure from the Arakawa Schubert, and then the problem happens in the tropics. In the tropics, usually the temperature stratification is conditionally unstable. That means the temperature profile is stable with respect to the dry parcel. So if the parcel is not saturated, it's stable, it's going down. But if the parcel is saturated, then the parcel can go up. So in general, the tropical temperature profile is conditionally unstable. And now you want to think about this kind of system. This is one grid. Let's say this is a 200 kilometer by the 200 kilometer box. And then in this box, a lot of convection is actually happening. However, like if we don't deal with those convections, then we have to wait until the whole grid saturated for the ascending motion to be happening. And then this is very crazy situation because it's very not realistic, like this 200 kilometer versus 200 kilometer box is completely saturated and the relative humidity is 100%. And then sometimes that happens, but if that happens, it makes a lot of instability and then it makes the model blows up. Therefore, we have to deal with these clouds somehow to run this model successfully. And then that's why, for instance, in the 1960s, Suki Manabe was invited by Smagorinsky to GFDL because in the 1960s, he was the only person who knew how to deal with this problem. And he in the Princeton, like he was sitting next to me, his office was next to me, and then he visited my office, almost every day, and then talking about his, those history. Sometimes it's gonna take 2 hours or 3 hours, same topic every day, but it's very, it's very interesting information about those kind of history of the climate model. And he told me that yes, that convective parameterization is necessary because otherwise it's gonna blow up. And recently we have two approaches to solve this issue. One is making this grid finer and finer so that one grid can capture the clouds or one grid can resolve the cloud. So this is the approach of the global cloud resolving model approach, but this is very computationally expensive. And then the other approach is just a convective parameterization. Okay? We need to understand, we want to have some kind of equation or some expression of the cloud behavior as a function of this area averaged quantity, like area average temperature, area average the water vapor, etc., etc. And I want to take this approach, and I want to use the most simple cloud parameterization to represent the convective behavior in observation. The parameterization I want to use is here. This figure shows, this is from the Brian Maves figure, and then this shade represents the precipitation, and then this contour, and then blue shade represents the column integrated water vapor. So you can see that the convective system is surrounded by very moist, rich envelope, and then it's kind of difficult to see this contour or the shade of this blue, but if you have a lot of moisture, then it has a strong positive correlation between this precipitation and then the background, the precipitable water or column integrated water vapor. So we want to use this relationship to explain the behavior of the convection. And for doing that, we're gonna start from the two equations, the dry static energy budget equation, and then also the moisture equations. Okay. S is the dry static energy. This is the enthalpy plus the geopotential. This is the dry static energy. And then P is precipitation. The QR is a radiated heating. And the H here is a sensible heat flux. And the angle bracket represents column integration from the surface to the tropical pressure. And this equation, the Q is a specific humidity. And then E is evaporation, and then precipitation again here. So we can say that the tendency of the column integrated dry static energy is balanced by the flux convergence of the dry static energy and the precipitation and the radiation and the sensible heat flux. And then this is the moisture equation. And we can add up those together to get the moist static energy budget equation. H is moist static energy budget, which is a combination of the dry static energy and the moisture. Again, angle bracket represents the column integration. And then here the S is surface evaporation plus the surface sensible heat flux, and then which we call the surface fluxes altogether. So the column integrated moist static energy tendency is balanced by the flux convergence of moist static energy and the column integrated radiation and the surface fluxes. And in the deep tropics, we know that the anomaly of the dry static energy is much smaller than the anomaly of the moisture, because in the tropics, the gravity radius is so big. Therefore, if you have any temperature perturbation, it's going to dissipate very quickly as the gravity wave, and there is no tendency of this term becomes very small. Therefore, from this equation, we might be able to ignore this term. Therefore, we can approximate the column integrated moist static energy budget equation like this. The column integrated water vapor is roughly balanced by the flux divergence of moist static energy plus D, which represents the diabatic source. The diabatic source is column integrated radiation and the surface fluxes. And then we want to analyze this equation, and we want to simplify this equation further and further by using the reanalysis data and also the satellite data. For this analysis, we use the TRIM 3B42 product for the precipitation, and then later on, I'm gonna also use the precipitation, which is simulated by the weather forecast model, the ECMWF model, to compare the behavior of the satellite observation precipitation and the simulated precipitation. And then, by the way, the precipitation simulated by this ECMWF model includes convective parameterization. So if there is some kind of discrepancy between the TRIM data and then ECMWF precipitation, that means there is something wrong in the convective parameterization. And for the other variables like temperature, moisture, we're gonna use the USRA intron. And we're gonna look at 6 different domains. For the for the ocean region, I want to look at Indian Ocean basin here, the Western Pacific here, the Central Pacific here, and the Atlantic Ocean. And then for the land continental region, I want to look at Africa and Amazon. And then this contour shows the column integrated divergence of dry static energy, which is roughly equal to precipitation. So you can see like this is pretty much like a precipitation pattern. So this, the reddish color means ascending motion is happening, and the bluish color is the descending motion is happening. And then we want to just looking at only the ascending motion, where the ascending motion is happening. And then we just looking at the JJA season for the time series from the 1998 to the 2012. And we did the regrading into the 0.5 degree or 1.5 degree. And again, yeah, we did the time series analysis, only the JJA of the daily quantity. Again, I want to look at this equation. I want to look at this equation, and I want to simplify this equation further. First of all, this schematic represents some feedback mechanism. Okay, you can compare the one case when the convection is not strong, and in the other case is convection is very strong. Now the convective system is organized in the very strong events, and in this weak convective event, the long wave radiation is emitted from the surface, and this is directly escaping into the space. However, if you have this stratiform clouds, or if the convection is very strong, this long wave radiation emitted from the surface is captured by the stratiform clouds. Therefore, the long wave radiation escaping into the space is very small. Therefore, by increasing the intensity of the convection, we're going to have the increase of the column integrated radiation. We have anomalously warming due to the strong convection, and this is positive feedback. We can say that as the convection becomes stronger, we have more stronger radiative warming, which increase the column integrated moistatic energy. Therefore, that is a positive feedback. And then there is another positive feedback happening in these strong convective events. Okay, in this strong convective event, gustiness happens, and then this gustiness enhances the surface evaporation. Therefore, we can say that as the convection becomes stronger, we have the stronger surface evaporation. And again, stronger surface evaporation means more column integrated moisture or column integrated water column integrated moistatic energy. Again, so this is the two positive feedback mechanism is illustrated here: radiation feedback and then surface flux feedback. Both are positive feedback.
What about the solar part?
Short wave radiation?
Yeah.
I think there should be some that I didn't separate the short wave and long wave, but I assume this relation is due to the long wave, but
I think mostly due to the long wave.
yeah, I guess.
That it wins
There
over a
certainly
slight
could
short
be a
wave
little bit of short
cooling?
wave too. No, the long ones.
I don't know. Maybe the short wave is very important.
I think Matt is talking about the shortwave shielding, which affects the ocean rather than the
Yeah.
atmosphere.
Yeah.
So that's not affecting
Okay.
the atmospheric budget.
Right.
Shortwave
It's
absorption
kind of possible, yeah.
affect the atmospheric budget.
Then could I ask, how does divergence of dry static energy, I'm curious how it relates to Greg Tripley's work. He has, the spool of,
Ape?
yes. Is it a very closely related concept?
The Greg's one is just a column integrated temperature normally, right? The ape is, and then.
I'm not sure what you're referring to here.
So, but the divergence of dry static energy is roughly equal to precipitation. So you can think that is a precipitation. That represents the vertical advection.
But then that's part of the energy being exported to high latitudes.
Yeah,
The
okay.
process Greg's thinking of.
Yeah, there's a lot of the energy winds up as geopotential in the upper troposphere.
Right.
And that tends to be trapped up there unless it's exported out to higher latitudes.
Okay.
It's actually up high enough, the radiative feedback is minimal.
Hmm.
Because radiation tends to maximize in the lower parts of the troposphere. If you get up too high, there's a level of zero net radiation,
Okay.
and a lot of the mass that's put up there is above that.
But how about like if you have the clouds there, then it's a kind of greenhouse effect here.
The cloud shield would be a little lower, and, the cloud shield that persists is a little lower than that, but some of the mass gets up above that, and if there is a cloud shield, it's not there all the time. It can be there for a while, but it doesn't necessarily drive the air diabatically to lower isotropic levels, so it tends to get trapped up at the higher levels.
Okay.
This is above like 355, 360, so it's up pretty high.
Okay.
Only the tallest convection in the tropics gets up there, but when it does get up there, the mass is stuck.
Maybe we should talk about it later.
Yeah.
Yeah. So this is like the verification of this schematic from the Toga board data. The y-axis, the first figure, y-axis is the column integrated radiation as a function of the column integrated divergence of dry static energy, and you can see the positive correlation between them. And then there is a positive value here, 0.11. This represents the intensity of this positive feedback due to the radiation. And the second plot shows the surface evaporation and then sensible heat flux as a function of the divergence of dry static energy. And again, this also has a positive correlation. This represents the gastiness component. And if you add up those together, we have very strong positive correlation. The y-axis is a diabatic source, the column integrated the radiation plus surface fluxes as a function of the divergence dry static energy, and then you have like the 0.2 slope here. So this is very strong positive correlation. And then this slope is very important for this concept. And again, this is the same figure from the Toga board data. And then this is from the satellite observation. This is another the PhD thesis, y-axis diabatic source, and this diabatic source was computed from the satellite observation. From the I use the Tristan's Herb data, and then also I use the C-flux, which is the satellite-based the surface flux data, and we have the positive correlation. Therefore, we can approximate the diabatic source as a function, linear function of the divergence of dry static energy like this, some critical constant gamma times divergence of dry static energy. Again, this small gamma represents the intensity of the positive feedback. Therefore, we can approximate the column integrated moisture equation like this. And now I replace this diabatic source here with the linear function of the divergence of dry static energy. And then now I want to use this relationship, precipitation versus precipitable water, to change this part into the precipitation equation. This is the figure from the Bredotten et al. 2004. Y-axis is the precipitation, and the x-axis is the column integrated water vapor. And then you can see that all the oceanic basin, we can have the exponential relationship. Therefore, we can say that the tendency of the log precipitation, the log, I'm taking log because this is the exponential relationship. Okay, tendency of the log precipitation is proportional to the tendency of the water vapor. And this pattern is, this relationship is very robust among all oceanic basins. This is from my analysis using the TRIM data. Y-axis is a tendency of the log precipitation. The x-axis is the tendency of the column integrated water vapor. For the Indian Ocean, Western Pacific, and the Central Pacific and Atlantic Ocean, you can see the positive correlation between those two. And therefore, we can approximate this equation by using this assumption, saying that precipitation tendency, the log of precipitation tendency, is proportional to the convergence of moist static energy plus some linear function of the dry static energy. So this is a simple model which I have right now, and I want to simplify equation further, but right now I want to verify this model. For doing that, what we're gonna do is, first of all, I'm looking at this two-dimensional plane. The y-axis is this value, the divergence of dry static energy, moist static energy, and the y-x-axis is this value, the divergence of dry static energy. Again, this divergence of dry static energy is roughly equal to precipitation. So this plot is saying that I'm taking the moist static energy divergence as a function of the kind of precipitation. And then in this figure, I just draw this dashed line whose slope is determined by this small gamma. Again, the small gamma represents the intensity of the positive feedback. And then in this plot, I want to compute the probability of the amplification of the convection. Okay, I have the time series, and then I have the today's precipitation, I have the next day's precipitation, and then I want to determine the probability, how much probability we have for this precipitation intensity. Okay, how likely the precipitation increase in the next day. And then this is a figure. Okay, if the data point is located below this dashed line, this corresponds to the positive side of this equation, positive of right-hand side of this equation. That means the positive tendency of the precipitation. We have very high probability of the increase in precipitation. And the opposite is the case when the data point is located above this dashed line. It's very blue. That means most likely the precipitation decrease in the next time step. And actually this pattern is pretty robust among the all oceanic basins. This is the Indian Ocean, the Western Pacific, and the Central Pacific and Atlantic Ocean. You can see the beautiful blue and red pattern. And then this pattern is delineated by this dashed line. And then what is interesting is that each oceanic basin has different slope. For instance, this has a 0.36 slope. This is pretty high. Again, this is the intensity of the positive feedback. But in the Central Pacific, we have the slightly negative value, 0.02. That means the positive feedback is not going to happen in the Western Pacific and also the Atlantic Oceans. And here, I plotted this positive feedback constant gamma as a function of the geostationary location. And again, this is the gamma is radiation, is a feedback due to the radiation and surface fluxes. You can see that over the Indian Ocean and the Western Pacific, we have a pretty high value of this positive feedback. But in the Central Pacific, we have the slightly negative value. That means the positive feedback is not happening over the Central Pacific. And then Atlantic Oceans, the value is very small. This is because over the Indian Ocean, this kind of like top-heavy stratiform clouds happen a lot, but over the Central Pacific, the convection not going to grow into that high. Therefore, the convection not going to grow into this deep level. Therefore, the positive feedback due to the long wave radiation not going to happen over the Central Pacific. Therefore, which doesn't have the positive feedback over the Central Pacific. And now, in this plot, I just plotted the rate of the amplification. So it's simply the d log p dt. And this figure is representing how fast this amplification or decay happens. And this figure is saying that if like the moist static energy convergence is very subcritical, it's far below this critical line, then this is very positive. That means the precipitation intensification happens very rapidly, and the opposite is the case. If the data point is located far above this dashed line, then this d log p dt is very small. That means decay happens very rapidly, and then this is robust among the oceanic basins. Okay, now I want to simplify this equation further. For doing that, first of all, we can decompose the flux divergence of moist static energy into the vertical advection and then also the horizontal advection. Okay? And then we can say that the vertical advection of moist static energy is just some constant gamma p times the divergence of dry static energy. And by doing that, we can combine the vertical advection to this the diabatic source term here, we can say that the tendency of the log precipitation is proportional to the horizontal advection plus some gamma minus some small gamma minus gamma v times the divergence of dry static energy. And I'm gonna explain the physical interpretation of this one. Okay, so again, this small gamma represents the positive feedback due to the radiation and surface fluxes illustrated in this schematic. On the other hand, this gamma V represents the negative feedback due to the vertical advection. Okay. Now you have two different omega profiles. Okay. In this case, because the convection is very weak, we have very weak omega profile here. On the other hand, if we have very strong convection, we have the same structure, but we have very strong omega profile. And then let's see that in this kind of omega profile, we have the convergence of the air happens around here, the middle troposphere, where the moist static energy is very poor, and the divergence of air happens in the very upper troposphere, where the moist static energy is very rich. So in this system, the moist static energy poor air is coming into the system, and the moist static energy rich air is coming out of this system. So this system causes net export of moist static energy. So this is just a damping effect or negative. More convection happens, more damping or more export of moist static energy. Therefore, we have the positive feedback, but this is cancelled by this negative feedback effect due to this vertical advection. Therefore, we have the effective positive feedback constant gamma minus, small gamma minus gamma V appears here. And now I want to show some scatter plot of y-axis is a it's a diabatic source, so radiation plus surface fluxes. I just computed from the ERA intron. And then again, x-axis is the divergence of dry static energy, or roughly equal to precipitation for Indian Ocean, the Western Pacific, and the Central Pacific and Atlantic Ocean. Again, we have very strong positive correlation and a positive line. This means we have a strong positive feedback happening over the Indian Ocean, Western Pacific, but we don't have that kind of positive feedback over the Central Pacific and Atlantic Oceans. And now I include in the y-axis the diabatic source minus the vertical advection as a function of the same divergence of dry static energy for different oceanic basins. And now you want to compare back and forth. For instance, like if you look at this Indian Ocean, okay, this is, we have the 0.36, the slope, and because of this damping effect, this positive feedback effect is reduced to the 0.24. And for this Western Pacific, 0.23 to 0.1. Therefore, like we over this region and this region, usually the radiation and the surface fluxes has a positive feedback which amplifies the convection. However, the vertical advection is just a damping, and therefore which reduce this positive feedback constant. But over the Central Pacific and Atlantic Ocean, it's kind of opposite happens. Over this is the diabatic source. Again, we don't have any positive feedback happening here due to the radiation. However, if you include the vertical advection, then you have the positive value here. That means because over the Central Pacific, the omega profile is very bottom heavy, that means more convection leads to more import of moist static energy. Therefore, vertical advection has positive feedback over the Central Pacific. And then that is the case over the Atlantic Ocean too. And then this is the map of those different feedback constants. Again, the first one is a small gamma. This is a positive feedback due to the radiation and the surface fluxes. And the second plot is a negative feedback component, the gamma V, due to the vertical advection. So if you, for computing the effective feedback, you want to subtract this minus this one. I mean, you have very strong positive correlation, but you have very strong damping effect over the Indian Ocean. But over the Central Pacific, like, it's kind of opposite. You have nothing or slightly negative feedback happen due to the radiation. However, we have the negative value of the negative feedback of the vertical advection. That means we have the positive feedback happening over the Central Pacific and also the Atlantic Oceans. So if you subtract this minus this, and then you get this figure. Okay, so now we have the effective feedback constant. This is taking account both the radiation and then the vertical advection. We have very strong, still strong positive feedback effect here, Indian Ocean, Western Pacific, but Central Pacific and Atlantic Ocean is not so strong. Therefore, by using this relationship, we can simplify the model like this. Okay? The tendency of the log precipitation is balanced by the horizontal advection and then effective positive feedback due to the convection is here. So now I just plotted the slope of this gamma minus gamma b here, and then y-axis, now I just replace into the horizontal advection. Then this works pretty well. Like, that means the horizontal advection is the primary importance for determining the amplification and the decay, and also this slope is another important ingredient to determine the amplification and the decay. Okay, so I want to summarize so far. Okay, what I did is I deduced a very simple model, and then I answered the following questions: when convection amplifies and decays, how fast convection amplifies and decays, and then what are the main drivers of the convective amplification and decay, and then those figures answer those questions. Okay, this figure shows that the convection amplifies when the advection carries the moist static energy into the system more than this critical value, and then damping happens in the opposite case if the point is located above this critical line. Again, the critical line is determined by the feedback between the radiation and the surface particles. Then we have the damping. And now we know how fast convection can amplify or decay. If that means if you have very subcritical value or very farther from this critical value into the downward, then you have very rapid intensification, and the opposite is true. If you have farther upward in this plane, you have very fast damping of the convection. Therefore, this model represents the rate of the convective amplification or decay very well.
And how did you compute those amplification rates in decay?
So I just first computed that. So it's kind of tricky because we know that around here, like sometimes increase, sometimes decays. Therefore, those have to be canceled out. Therefore, if I just take an average, then we might have a beautiful figure, but that's kind of cheating. So what I did is, first of all, I took the absolute value of the log of the d by dt of log precipitation, and then computed the absolute value. And then if the mean value is negative there, then I just multiply the sine function.
Okay. Yeah, maybe we'll talk about it more.
Sure. And what are the main drivers to determine the convective amplification and decay? So there are two important ingredients happening here. We have the positive feedback due to the long wave radiation, which is prevented by this stratiform clouds, and then we also have positive feedback due to this gustiness, and then this is the positive feedback. This is counteracted by the negative feedback due to the vertical advection. This is damping effect, and then those two are canceling out each other, which determine the critical constant. And then if the horizontal advection carries the moisture into the system greater than some critical constant, then we have this amplification. The opposite is happened when the horizontal advection carries the moisture into the system less than some critical value determined by the feedback effect. Then in that case, the convection decays. And then this is the case among all oceanic basins. And now I want to show a little bit extra work. using the ECMWF precipitation instead of the trim precipitation. And first of all, I want to show the result over the ocean. It's not interesting. Everything is same. We have the Indian Ocean, Western Pacific, the Central Pacific, Atlantic Ocean. This works pretty well. But if we look at the convection over land, it's going to be more interesting. First of all, I want to show you the trim data, and then I want to show the predictability over land. This is over Africa, over Amazon, and then we lose a lot of predictability. That means our moist-static energy-based model doesn't work over the continental regions. And we found out the reason why it didn't work is that the assumption that the tendency of log precipitation is proportional to the precipitable water tendency is not valid over land. For checking that, I plotted here just a probability of the sign function of the precipitation tendency is equal to the sign function of the water vapor tendency. So if whenever precipitable water increase, precipitation also increase, then in that case, it's gonna be 100%. If the precipitable water and the precipitation are completely random, it's gonna be 50%. And then you can see that over the ocean, we have the high probability. That means the precipitation over the ocean is regulated by the precipitable water or water vapor. However, we have very strong land-ocean contrast here. And over the land, we don't have that kind of strong correlation between those two. However, if you replace the precipitation data into the ECMWF simulated precipitation, again, the ECMWF precipitation is simulated using the convective parameterization, and now you have this land-ocean contrast disappears. We have very high probability even over the Africa here, and then we cannot see any land-ocean contrast here. Therefore, this means that the convection over land behaves in the exactly same way as the convection over ocean in this ECMWF precipitation. Therefore, I plotted this predictability figure. Again, this is for the trim precipitation, and then this is the ECMWF precipitation. Now, we have a lot of recovery of the predictability. Therefore, like moist static energy budget, the framework works kind of well comparing to the trim data in the ECMWF precipitation. Okay, and then this indicates that the ECMWF precipitation, which is simulated by the convective parameterization, could be wrong in a very specific way, that the convection over land in that model behaves in the same way as the convection over ocean. And then it's maybe because we don't have any tuning process over land, we don't have observations, and then a lot of tuning, a lot of convective parameterization itself was developed based on the observation over the ocean. So we don't know what's happening over the land. So this might be the cause of this discrepancy. This is all what I have. Thanks. Any questions?
We know that the water circulation is correlated with regions, the upward motion of water circulation is correlated with the regions where deep convection is predominant.
Okay.
So the question is, does the water circulation deepen the convection, or does the convection deepen the water circulation?
That's a good question. Yeah. Or maybe the MJO could deepen, like it has the same, like when the.
It's the same question.
Yeah. Right. Yeah. And no idea, but the. I would say that it's a very chicken and egg kind of questions, and then I don't have any good answer. But I think that the omega profile is driven by the SSD gradient, as Larissa said in the 2009 paper. So in that view, first of all, SSD determine the omega profile. Therefore, and the SSD determine the local circulation. Therefore, we can say that Walker circulation determines the variability of the omega profile. So I think like it's kind of top down from the large scale to shorter time scale. It's kind of my speculation, but I don't know.
So, this is a pretty vague idea, but can your techniques be used in general to assess whether, in a given numerical model, which convective parameterization might be better than other ones?
I think like, for instance, like this framework should be very like easily applied to that kind of things. And then I quickly check like, for instance, this model, like this like GCM, and then which couldn't produce this kind of land ocean contrast. And so this is kind of one way to qualify or evaluate the convective parameterization. And about like GM, like this kind of moist static energy stuff, I think like we should look at, I think yes, we can use that framework also to evaluate the behavior of the convection.
That's what Kuni's postdoctoral proposal is about.
Yeah.
That's what he's working on.
The trim product over land and also the temporal variability of trim. Can you just comment on both of them? I don't have any idea. I don't know trim at all, but my understanding was that it's a different product, it's a different algorithm over land and water.
Yeah. And then it's based on the IR, the infrared instead of the microwave.
Okay.
And I talked to like many people in NASA about it, and then yeah, like it's kind of questionable if we can trust the trim data over land, but we are sure that the trim data is much better than the ERA trim. So it's but yeah, so like I think what I should do next is I think I should look at like different data sets of the precipitation and then do the same analysis.
What's the temporal sampling? Once it goes over, what's the?
It's a geostationary. So over the land, it used a geostationary satellite.
Oh, okay.
So we have like a 3-hour temporary resolution. But again, it's a IR data, so I'm not sure. More question?
How about the age-old one? Is an answer emerging in the convective modeling community for the question of how much parameterization and how much direct representation is appropriate? Is there a magic number? Is there a threshold? Like above 20 kilometers resolution, you have to have convective parameterization. Below 1 kilometer, you never want it. What's happening in that?
So there is a zone called the gray zone. And then in the gray zone, like what's happening is that like if sometimes like in a large scale thing, like of course like over the 25 kilometer grid, you need the parameterization. And below the 25 kilometer, but I think the Greg is more familiar with that, but below the 25 kilometer, it's kind of questionable. You know, you can run the model with that parameterization, but I'm not sure if that is very correct way to do it. And then we know that it's underestimate a lot omega profile due to like some kind of crazy, the pressure gradient, like pressure gradients kind of artificially created by wrong grid size. And so like 10 kilometer, 20 kilometer is called the gray zone, and we don't know about that area. And less than the 10 kilometer, we are maybe fine. So
the 10 kilometer updrafts are not too bad?
Depends what you're looking at.
Yeah.
I think it depends on where you are, because the problem with the 10 kilometer updraft is that if you're out in a region where the Rossby-Reyes deformation is 100 kilometers, then you're going to project a significant amount of that heating right onto the rotational lows. And that's where you get in trouble.
Okay.
So in the tropics, you can probably use a 10 kilometer resolution where the Rossby-Reyes is huge.
I see.
And it won't really make that much difference.
Okay.
But when you get up to higher latitudes, it really matters.
I see.
Oh, that's interesting.
But in high latitude, like we don't have so many convection.
large scale dynamics is more what's driving things in the high line.
Right.
Yeah.
For that reason.
So that's why maybe we can use the 10 kilometer for kind of wrong reason. But we still don't know. And then we have no idea like we should use parameterization or not. Some people some people do that, like run the model 25 kilometer or 50 kilometer without convective parameterization. And the behavior looks kind of same, some sense. And sometimes like MJO is kind of good in that kind of sense, without convective parameterization. So we have no idea what we should do.
Any other questions, or? Okay, let's thank Kuni. Thank you everyone for coming, despite the strange time.
Thanks for coming.